everyone. I assume we're recording now. Great. Oh, we're recording, but I didn't share my screen. Let's share screen. There you go. All right. Hello, everyone. I hope you can see me. If you can't, let me know, because I only have slides in front of me. So just in case some of you think, these knights and knaves problems are things you can just ignore, or you think we're joking. We're not actually going to put this on, and we're not going to test you on this. There's going to be at least one question on knights and knaves in the midterm. So just letting you know, these we will test you on these little problems, right? They help with formalization from English to logic and how you can reason in logic and then interpret it back in English. So we will use some of these. So I recommend you look at the previous exercises or look online where we've posted some CalcCheck documentation which covers how to do these kinds of problems. I think they're also covered in the book, and they're pretty popular if you want to look them up. But the idea is we want to test you on equivalence and on negation in particular, right? So some things you should definitely be comfortable with. So let's click next. All right. So just as a reminder, there are two cores for this class, right? And you are welcome to watch the videos for either one, and they're run at the same time. So if one presenter doesn't click with you on a particular topic, you can look at the other, and you can watch both, and everyone has a different flavor. So do as you like, right? No big problem. Okay. So let's just recall what we were talking about yesterday. So we had substitution, which let us just the operation, which was essentially grafting on trees. So you walk along a tree, and everywhere you see a leaf, you cut that leaf out and put a new tree in. All right. Now there's this inference rule of substitution. All right. So if you notice here in the second line, all right, let me just draw that for you. Right here, this one, every hint between a calculation is supposed to invoke a theorem. Right? We're invoking the theorem a plus minus a equals 0, right? But there's a problem here, right? This one and this one, they're different symbols, right? So 2 times y is not the same thing as a. So this unary minus is talking about a, and we don't have any a's at all. So we can't use unary minus, right? Unary minus just says whenever you have an a and a negative a, they cancel out. So we can't use unary minus. The substitution rule, if you remember from last time, says if E is a theorem, all right, then E with a substitution is also a theorem. Okay. So if you ever have a theorem and it has some variables, you can substitute. That's what the substitution rule says. And so for unary minus, we make a substitution that a becomes 2 times y. And so now we have this new theorem, which is 2 times y plus minus 2 times y equals 0. And we can use that as the hint. All right. So that's what substitution is about. All right. So you want to use something that looks like a theorem, but the variables or instantiations are not the same. And so really what you're doing under the hood, like theoretically, is you're using the substitution rule, substitution inference rule, okay? When you're substituting in the middle, like in the body of an expression, such as right here, here we're doing subtraction, we're turning this minus into a plus, right? So we're changing this expression into this one, okay? So when you want to do something in the middle, right? Well, subtraction talks about the main operation of subtraction is this minus, and it gets changed into a plus. But here, the main operation is already a plus, all right? So it's already a plus, all right? So it's you can't use subtraction directly. You need to go into the middle of the body, up, make the change, and then come back to the outside of the body, right? And this kind of rewrite is under the name Leibniz, right? So these are just the theoretical foundations for why you can do a substitution in the middle of a theorem, right up here, or why you can replace equals for equals hidden, nested within expressions, which is this one. Okay. So these are covered in chapter 2 and at the beginning of chapter 3, and we'll come back to them later on. But I just wanted to mention the theoretical foundation that allows you to do these things. All right. And as we mentioned last time, substitution is closely related to assignment, right? Some people would say assignment in a programming language is in fact it means or it denotes a textual substitution, right? So a program is a sequence of instructions that the computer carries out, and every time it performs a step, what it's doing is it's every time it performs an assignment step as it's doing a textual substitution to change earlier text you wrote. All right, so we'll get to that a little bit, and then we'll finally get to the core of this class, propositional calculus. All right, so hopefully we'll get to a more formal part of that today. Some of you are texting me. Let me see what you are saying. Word problems are in chapter 2, so please look into chapter 2. There's a lot of problems there, and I think chapter 5 or 6 also has word problems. So there's a lot of word problems throughout the book. Chapter 2.4 specifically has the title Modeling English Propositions, so I highly recommend you look into that. And later on in the future, we'll get to section 9.3, English to predicate logic, to how to use these formal approaches to show that certain functions are continuous with epsilons and deltas, but maybe later on in the future, not anytime soon. All right. Okay. So just a quick reminder of how textual substitution works, right? Here's an x, and here's an x, and I'm just going to replace it, right? Here, I'm going to replace every x. Here's one x, and so it becomes z plus 2. I replace every x. Here's an x. I have to put in parentheses, otherwise it means something else. So here I can simplify. Here I cannot simplify. Right? Here I try to replace an x. There is no x right here. Okay, so substitution binds strongest than other operators. Okay, so that's what the last phrase means. Right. Everything we've covered so far will be on the midterm, just for the person who just asked. All right. We also discussed last time simultaneous substitution, which means do things at the same time. So I have x plus y, and I replace every x with y minus 3. All right. So let's. Oh, sorry about that. So every x becomes y minus 3. And every y becomes y minus 2. Okay. All right. This is different than sequential, which means do one then the other. So here, every x becomes y minus 3. Every x becomes y minus 3 happens at the very beginning, and then we do y becomes z plus 2. Right. So the inner one just replaces every x with y minus 3. But now we have two y's, and so we get one right here and one right there, right? And so these are completely different, right? So this is something just to be aware about, okay? This is, and in programming, you do have the idea of doing operations concurrently or sequentially, and they're not always going to be the same, right? So that's the relationship there. So this is substitution, what I mentioned earlier. So here it is again, just as a reminder before we use it. Sorry, before we actually use it. So remember, it just lets you change values, right? So if I have here, the theorem is about A, I changed it to 3 times B in both places, right? The first one's the theorem, the second one's the theorem, right? So these rules, as it were, just say, if you have stuff that's true, then you can continue to have true stuff with the following manipulation, right? So if E is true, then E with this substitution is also going to be true. All right. I'll get back to all these questions on the midterm at the end. All right. So instead of pausing every moment or so. So as I said a moment ago, an inference rule just says, you know what? If I have all of these things that are true to begin with, then then a particular manipulation of these true things is going to be true again, right? So in a sense, an inference rule is like a theorem, except the theorem will say, if this thing is true and this thing is true and this thing is true in a particular state, like when you choose particular values for variables, right, then in that particular choice, the conclusion will be true, right? Whereas then inference rule says, if you have these, right, and they are known to be true, then the conclusion will be true in all states. So the subtlety is the distinction is very subtle. One of them talks about all states versus talking about a particular state. So we'll come back to inference rules later on, but it's important you know at least what they are for now. And there's since we're skipping over them a little bit, they are covered extensively in the abridged lecture notes online. All right. So let's just look at a few more examples. So here, A, right, we just replace it with A plus 0. Sorry, we replaced every A with 3 times B. And so that gives us a new theorem, right, which is this one right here. All right. So all we did was we replaced every A with 3 times B, and we have a new theorem now. All right. Here's another one down here, and we replace every Z with X plus Y. Right. So don't worry about the more complicated example if you find it too complex. But the idea is you have an expression, all right? You have an expression right here, and then you just make a substitution, and it continues to be true if you started off with a true theorem. That's all. All right. So you're instantiating some variables, if you will. All right. So the important thing to remember is that X is a variable that you're changing. You don't get to change parts of the term. You only get to change a variable. So here we changed only A, right? We didn't change a sub-expression. We changed the variable, right? So this is part of how textual substitution works. Right? All right. So, and of course, when you get to simultaneous substitution, instead of X being a single variable, you can have, oh, sorry about that. You can have X being a variable list, right? So let me get you an example. In a moment, I'll get you to an example, all right? So if you notice, substitution talks about a generic expression that we're going inside and changing just variables about it, right? So here we have X plus Y, we have a list, all right, for X comma Y, and we replace X with B and Y with 3, all right? So let's just work this one out just so you can see it, all right? If I have X plus Y plus equals Y plus X, all right, then when I change it, the theorem I get, right, when I do the substitution B plus 3 is B plus 3 equals 3 plus B, right? So nothing terribly difficult, all right? But the fact that I get this as a theorem follows from the symmetry of addition along with substitution, okay? So we've talked about substitution. Now we're going to talk about our first logical operator, all right? If you want to check that something is true and it involves variables, then normal thing to do is to say, let me evaluate what it is at that variable, right? So for example, X equals X. How would we evaluate to check when this is true? All right. So we could say 1 equals 1 is true. All right, great. 2 equals 2 is true. Great. Oh. Sorry about that. Oh. My apologies, still not accustomed to this new tool. So you can say 1 plus 1 is true, all right? And then you can also say 2 plus 2 is true. And then you can also say 3 equals 3 is true. All right. Sorry, these are supposed to be equals. And equals. Anyhow, so you can check these equalities are true for each possible value of x, but then that could take a really long time, right? For every possible value of x. So instead, we know that x is always going to be equal to x, and so we say that's just a rule we have. It's an axiom. It's a God-given truth, and so you don't need to check it, right? Likewise, if x equals y, then this equality itself is equal to y equals x, right? Remember, equality is a Boolean operation, right? So equality takes two arguments, right? Anything of type t to t, and it spits out a Boolean, all right? Okay, so this is a type of equality. It takes two things of a particular type t and returns true or false. So here, x equals y, this is either true or false, and y equals x is either true or false. And the value of the left-hand side is going to be equal to the value of the right-hand side. Okay, so that's all that says. Right? This one and this one are going to be the same. Right? The transitivity rule just says if you have x equal to some intermediary y and y to intermediary z, then you can stick the pieces that are the same, and you get the leftmost part is equal to the rightmost part. So when you have a calculation and you have first step equals second step equals third step equals fourth step, transitivity is what lets us conclude that the first one is equal to the last one. So this is transitivity, right? And remember earlier we talked about going inside an expression and substituting. That's what Leibniz lets us do, right? So Leibniz rule just says anywhere inside an expression E, right, you can replace equal things with equal things, all right? So I can walk inside, find something that's equal, and change it up. Right? So this is the theory of our calculational approach, and we'll come back to it from time to time. Right? For now, it's really important to understand 1.2 and 1.3 at least, and we will definitely come back to 1.4, 1.5, Leibniz and transitivity. Right? So let's actually use Leibniz rule in action. We want to show that minus a times b, right, is going to be the same thing as a times minus b, right? So essentially, we're just swapping things around. Yeah. The very first step, right? Well, we have a minus b everywhere, right? So we want to get rid of that. So our context includes this times b and this times b, right? But 1520 doesn't talk about a multiplication, right? So this one, right? No multiplication, right? So 1520 doesn't have a multiplication in it. So, sorry, it has a multiplication. What I mean is no multiplication on the left-hand side, right? Which is what we're trying to do. We're trying to say, hey, negative a equals negative a times a, but this main thing has a multiplication, right? The outer one, right? So Leibniz lets us go from the outer blue boxes into the green inner boxes, make the changes there, and then everything inside the greater scope stays the same. That's what Leibniz lets us do. All right. Leibniz is implicit in the calculational method. Otherwise, there's an alternative to the calculation method called proof trees and natural deduction, which we might see in a few slides. And things grow a bit. So in this alternative style, you have to use Leibniz. You can't hide it in the notation, right? So the notation hides Leibniz, but that we are using it under the hood. All right. So we'll come back to these things since they are a bit vague and fuzzy. We'll come back to them. Right. The second part, we use minus 1 times a again. Right. This time we're also doing Leibniz, but now we're choosing what a is. Right. A is now going to be the value b, right? We've changed what a is by using substitution as well as Leibniz. Okay? So just some things to be aware about. So this is what I said a moment ago about proof trees. So when you apply rules, right, in the calculational method, what happens when you apply rules is that you get a nice, lovely calculation, right? This thing equals this thing equals this thing, and it's really nice, and it's very handy. And if you do calculations inside calculations, so with Leibniz and substitution, you get this box over here. The idea is that you chain equalities, and the application of the inference rules Leibniz and substitution happen under the hood. Okay, but if you use this idea of stacking rules on top, right? These so-called proof trees, because sometimes they diverge and branch out, as it were. So down here, for example, all right, we want to show that two things are equal. Well, to show these two things are equal, we notice that the outside parts are the same, and because the outside parts are the same, for them to be equal, the inner parts should be the same. Right? So we'll show that x with a substitution is equal to y with a substitution. So how do we do that? Well, these guys are going to be the same. Well, the substitutions are the same. This substitution is the same thing as this substitution. So we're applying a substitution to an expression, and we want to know if that expression is going to be true. Well, if it was already true, then a substitution would make it true. And this is the substitution inference rule. Right? So the idea is you build up these trees if you're so inclined. But we won't do that in this class. Some logic classes like to do it this way. But as you can tell by the boxes, the boxes are much easier to read and to write. And these theorems 1.5 and 1.1 are implicit under the hood. They justify why things work. They are a foundation. Whereas down here in these trees, you have to use them. Otherwise, you can't make progress. Right? So the presentation hides these details away from you. It's pretty neat. Okay. So as I mentioned not too long ago, right? A state is just an assignment of values to variables, right? So here's a state called S1. In this state, x becomes 5 and y becomes 6. These are the values associated with the variables. So if you ask me what's x minus y plus 2, I evaluate it in a particular state. I say, well, what's x? X is 5, great. What's y? Y is 6, great. So 5 minus 6 plus 2, that's 1. I found the value of an expression, right, parameterized by a state. I need to have a state to evaluate the expression. Okay, and so this idea of evaluating expressions with respect to a state is again really, really close to programming, right? Because if you have a program, you ask, what are these global variables? So x and y are global variables that were declared somewhere, and I want to know in this particular context, what are the values of these variables? And so S1, the state, is essentially a computer memory state. But the idea of a state as values associated with variables is much more generic than programming. They just happen to coincide. All right. So other logic classes would also call these things states. All right. Some of them might call them environments, or if you're from Europe, you might call them a store, right? Like a memory store. Right. Some of you have texted a lot. Okay. You're just chatting among yourselves. All right. Okay. Great. Great. So as we said at the very beginning of this class, proofs are programs. And if you're an eager beaver and you really want to know what do I mean by this idea of proofs are programs, you are welcome to go to chapter 7. Chapter 7 will explain this idea in under 10 pages, if you're so interested. But because we keep saying proofs are programs, we should be able to bring this on a solid foundation. What does it mean that a proof is a program? Well, if I have a program called C, right? So I have a program called C right here. This is my program. What does it mean that my program is a proof? Right? Well, a program, you say my program has some precondition that it achieves, right? You write a program because you want something to happen. Right? I want colors to pop up on my screen, or I want some code to be checked. I want something. I want to get something done. Okay, but sometimes to get Q, the variable Q accomplished, you need to have some basic assumptions. Right? You need to have some basic assumptions P. Right? So, for example, I will post a computer program C could post your video to YouTube, provided, all right, so Q is posting it to YouTube. That's what you want to get accomplished. And P is provided the video is a particular size and length, right? If it's too long, you're not going to post it. And if it's too big, it might not fit in with the parameters, right? So you can have some preconditions or provisos P, and then you run your program, and you have some guaranteed conditions Q, okay? So the idea that we say, every program is written with these two things in mind, right? Whenever you write a program, you have some goal Q you want to accomplish, and some assumptions P. Sometimes you have the empty assumption, which is still an assumption. So these are always parts of programs. Sometimes you see these as comments, like X should be positive. The user gave me a valid email address, and stuff like that. It's not a malformed URL. So sometimes you see these as comments in the program, right? And the idea that proofs are programs is that when we have these precondition and postcondition, the program is a proof, right, that we can start from P, right, and we can get to Q, and that the program, right, the program is a particular implication, as it were. All right, starting with some properties about my variables, my global variables, I can perform some sort of manipulation to the global variables to get this new property. Okay, so programs, right, are proofs of these particular theorems. A program proves this theorem. All right, so let's write that out. A program, all right, proves a theorem, okay? You have a program, and it proves this theorem, all right? So this is covered much more in other classes, but we're gonna do some significant work with these ideas, all right? And again, chapter 7, if you're so inclined, all right? Sorry about that. Okay. So just as we've done before, we're going to when we have a chain of equalities, we put these right here on the side, all right? We put things on the side, and that's how we make our proof. But now we're going to have an implication that's parameterized. All right, so these things will have quills on them on the side, as it were, and we'll show that if you start, for example, if you start in the true state, right, so the empty proviso, and then you perform this program, x becomes 1, you end up in this state, that x is now 0 or x is 1, okay? Of course, you normally don't know what your starting provisos are. You usually have an idea of, this is what I want to accomplish. I want this, right? How do I get this? How do I get my goal? How do I achieve my required goal? And again, this is in other classes. You'll find out, oh, I need this program, okay? So to get this goal, I need at least this program. And then you simplify using something called the assignment rule to find out that the precondition is just true. All right. So what does the assignment rule say? What does the assignment axiom says? The assignment axiom says, if you have something you want Q to be true, and maybe Q mentions some variable X, then the only way Q is going to be true is if Q was true before you updated the value of X. So before you did an update to X, before you said X becomes E, Q was true, okay? So the only way Q is going to be true after an update to X is if it was true before the update was there and X has the value of the expression E, okay? So it's a bit counterintuitive, but if you practice a little bit with it, it will make more sense, all right? We'll see how time is, and maybe we'll come back and do some of these actually do some of these in person, all right? Okay. Of course, in programming, you don't have just assignments. You have sequencing and conditionals and loops, and you have a lot of different things in programming. For now, just to make things accessible, especially to non-programmers, we have an assignment which just says, X gets this value. So I have a value and I'm going to name it X. I have a cabinet in my home labeled X, and I put values in there if you like. And then we're going to use this thing called sequence. Right? Sequence just means that you read it as then. So do command 1, then do command 2. Okay. So if I have a goal R, I can break it into pieces, right? Separation of concerns, or if you like, or divide and conquer. I break my goal, my required goal R. I break it into 2 pieces, and I say, all right, I can get R from having Q, and I can get Q from having P. Okay, and so then again, it's transitivity. And as you'll see later on when we get to implication in detail, implication is transitive, and so these parameterized implications are also transitive. Okay. All right. So we can P gets us to R through a sequence. If P gets us to Q to some expression Q through the first command, and then from Q to R through another command. Okay. And just as we talked before about how transitivity of equals shows us why the top of an equation, right? So if you like, I have E0, right? And then I have equals E1, then I have equals E2, then I have equals E3, right? Just as using this gets us to E0 equals E3, right? Okay, so this kind of calculation gets us to show that the first thing in the calculation is equal to the last one. Likewise, with the dynamic logic, with the programming, P with a bunch of parameterized implications gets us to the last one, but we sequence them along the way. Now, this is a subtle point. When we had a bunch of equalities, there was nothing to remember. The equalities were, there was only one equality, right? When I say X equals X, how is X equals X? Well, it just is. There's only one way. But to show that P implies Q using a program, well, which program are you going to use? For example, if my goal is to get true, my goal is to get X equals 5. I want X to be 5 at the end of the program. I can do that by running a loop that does nothing for 1,000 steps, then sets X to be 1. Okay, or I can just set X to be 1 directly. These are different programs, and which one I choose matters. So here for program logic, we keep track of the choices, C1 and C2. These are our programs. So how I got from P to R actually matters. Okay, and so this is a subtle distinction between proofs and our programs, but it's essentially the same thing, but in one case you remember pieces, in the other case there's nothing to remember. Right? And again, this is in the abridged lecture notes if you want to know a bit more about this idea, and in chapter 7 of the book. All right. Okay. So when we do this in CalcCheck, there's nothing essentially new, with the exception. So you have a bunch of equalities and a bunch of equalities, but now some of them will have these implications with a program right in the middle. Okay, right. So the way you read these, and I drew that arrow earlier, but I forgot to reference it. You read these arrows like this, right? You start at the very bottom. Okay, so this is really important. Right? You start here. This is where you start. Okay, you start here, and then so let's read this together. I have X equals 12. This is my goal. I want X equals 12. The first thing I decide to do is I use the assignment rule. Okay, so I write this line down. The assignment rule says do an actual substitution. All right. And notice that this is a becomes / colon equals, and this is just a colon and then an equals. They're different, right? Up here is a is a Unicode, and down here is two symbols beside each other. Okay, this is just to remind you that one of them is programming and the other one is math. All right, so just trying to remind you of this subtle distinction. Okay, so we did that step. What's the next thing to do? Okay, so now we do substitution. Substitution just says find every x and every x right here, find that x and replace it with a y, with y plus y. And so that gives us, that gets us all the way here. Okay. Now, we want to be able to use, our goal is to prove this theorem, which has two assignments. And so the only thing to do is to use the sequence rule. And so we do a bunch of preparation in order to get us close to using the next assignment rule. And then again, we repeat the same process for the first assignment. And we essentially, we take what is required and we shove it through the sequence rule and through the assignment rule to get other things. And we keep pushing up, 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 up until at the very end, we get that x equals 5. Okay, so this is in the exercises and homeworks. And we also suggest there that you start at the bottom and shove things up. All right. So we did a bunch of steps here just to make it clear, but some of them could have been squeezed in into a different fashion, right? So we'll look at that in due time. Right? So make sure we have time for our other things. So we'll eventually, our programming language for now, our goal is not to teach programming or to focus too much on it, but the class is applications of discrete mathematics. So we're going to cover practical problems, practical, of ladies and tigers, but we're also going to cover some things in the lines of programming. So here's what conditionals look like in other languages. Our language doesn't have conditionals yet. In a few weeks, we'll come back to this issue. All right, and of course, I'm not going to talk about what's going on in conditionals, but we'll get back to it in time. I just want to let you know that you're not going to be doing just boring things like assignment and sequence. You know, we'll get to more interesting stuff later on. And this is all calc check. Like, so these things are understood by calc check, so that's pretty neat. Okay, so here's an example of how you can use it, right? So a conditional is a branch that says, you know, if something's true, do this, otherwise do that, and we're going to do some actually non-trivial programs by the end of this class. So even on the exam, we're going to have some non-trivial programs that will accomplish interesting things, like finding paths in graphs, right? So it will be sufficiently expressive language, and everything will be correct because you'll be able to prove it. So really neat things, but no need to worry about it. So you do have a midterm coming up next week. All right? This is what all of these text messages seem to be about. So you do have a midterm coming up next week, and here's the slide in front of you. If there is any of these words you're not comfortable with, I recommend you study up what these words mean. So you definitely want to know what is associativity, what is symmetry, what's an identity. All right, so you really want to know what these words mean, okay? And not just in the context of numbers, but in general. What's a distributivity? What's a zero? Okay. What's the difference between unary and binary? You really want to know these for the upcoming midterm. So what we're going to do is we're going to give you an assignment, right? So which is like a longer homework, and the assignment is going to prepare you for the midterm. But you really do want to know all of these ahead of time. All right. So that will be extra stuff for you to help you practice. And here they are filled in, and I won't go through them. We've talked repeatedly about them, but you definitely want to know this, what these words mean, and I hope you've done sufficient practice in the exercise we provided you to get you ready for the midterm. Okay. All right. So let's look at cancellation of plus, because unlike the first three, cancellation of plus is kind of special, right? You'll notice that these guys are just equalities, whereas this one has an equivalence, right? So you definitely need to be comfortable with basic uses of equivalence like 15.8. So here's a times 0, and we want to show that it's equal to 0. One way to do that would be to say, okay, let me introduce, because of cancellation of plus, I can introduce a dummy variable. So I'm just going to introduce this dummy, a times a and a times a. Okay, so I just introduced this piece, and then I do distributivity and I simplify. Okay, but notice cancellation of plus says if you want to show two pieces, you can introduce anything you want as long as it's the same. Okay, anything as long as it's the same. All right, so let's look at a few examples to see what we mean. So here's the same thing again, but now we're going to introduce a times d plus on both sides, right? So you have this part, right? And so if you want b equals c, you can introduce an extra shared part. And the shared part we introduced is a times d. And again, we can perform distributivity to pull the a's out. We have a plus 0 on both sides, and this is equal, right? And so this thing is equal to true. Okay, this is a reflexivity of equals, which is true. All right, and again, you can introduce anything you want over here. That's why it's a cancellation law. You can take things out and put them back in. Pop in, pop out, whatever you like. Okay, so let me show you one more example of this. Okay, so this time we're just going to introduce 42. Okay, so a times 42, and it's the, I shouldn't have erased them, I suppose. It's just, as long as they're the same pieces that are being introduced. So we introduce a times 42. The important part is we do a distributivity, which lets us pull out the a's, and then we have identity to get rid of the plus 0, and then we have the same thing, right? X equals x, right? Or a equals a, right? And so this is true, right? So these are just useful features that you'll gain more understanding and comfort with as you practice. So hopefully you've been doing the exercises, and even though they're not for marks, but you have been doing the homeworks, which are graded, and there will be a larger homework called an assignment to help you get ready for the exam. Alrighty. Let me get rid of this. Okay. So, as mentioned repeatedly already, this operation is called equivalence, or equals, if you like, and it's just equality on the Booleans, right? That's all it is, okay? The reason we decide to write it this way is because of precedence, okay? So remember precedence, right? So we treat equality to be higher than equivalence. So that's the main reason we have two names for the same idea. Equals is higher than equivales, all right? And this means we don't have to write as many parentheses. So that can be very convenient, right? And another thing we do is we treat equals as conjunctive, if you remember from the last lecture, and we treat equivales as being associative, all right? So just quickly to remind you what that means. So we say x equals y equals z, right? To mean x equals y and y equals z. Okay, so this is what it means to be conjunctive. It means for each equality, for each relation being used, you put an and the two pieces in the middle stay there. Whereas associative means no, you instead either parenthesize this way or parenthesize this way. Okay, so and again, this is also covered in the abridged lecture notes and in the book. So this table of precedence is taken from the book. All right. Okay. So here's a reminder of what the three main inference rules are that justify how things work in the calculational style. The last one, if you have an older version of the book, you might not see it. It's called equivalence, but it just says if x is a theorem and you're starting with y, and you showed that y is equal to x, then y is also a theorem. Right? So it just says the theorems are essentially the same thing. Right? If I have a theorem and I reduced some problem, I reduced some expression into that theorem, then the original one's also a theorem. That's all it says. Right? So it's nothing too complicated, and we've been using it implicitly throughout. Right? So as I mentioned earlier, transitivity is what lets us conclude that the top expression is equal to the bottom of expression, right? So you start at the top and you slide down to the bottom, and so they're equal, okay? So transitivity is what justifies this sliding down, alrighty? Okay. So as I've mentioned before, a theorem is an axiom, the conclusion of an inference rule, and then right here in gray, this is the equivalence rule, which just says if you have A is a theorem, and you showed that B reduces to A, then B is also a theorem. That's all. Right? So nothing too much. We're going to be doing things algebraically. We're not going to be doing things with regards to states. If you want to show two expressions are equal, you don't have to look them up for every variable and check that they're equal on every variable. You just see if you can apply a number of these equational rules to reduce to true, for example. All right. So that's the approach we're going to in this class. And because we're focusing on equality as an operation and not as some auxiliary concept that we can disregard because we're going to evaluate, we're going to focus, we're going to start by looking at the properties of equality. All right. So for us, equality is the primitive operation. That's why it's an equational logic. Everything is centered around equals, right? Because it's really easy to reason with equals instead of other operators. So if you recall a moment ago on the previous slide, I had all these inference rules, and inference rules, you stack them on top of each other to derive new truths, right? So I apply Leibniz to substitution, and I stack them on top. The problem is rules are read from top to bottom. They say if the stuff on the top is true, then the stuff on the bottom is true. So it's an if-then relationship. So it's an implication, right? So it's not an equals. You can't go the other way around, right? Our focus on equalities means we can go up and down however we like. And because we're using an equational style, there's no real distinction between up and down, as it were, right? So just as addition is associative, you can move the parentheses around. Equivalence is also associative. You can move the parentheses around, right? From here or here, okay? Symmetry means I can flip the argument around, just like x plus y is the same as y plus x, right? So I can say P equals Q is the same as Q equals P, okay? But because of associativity, I can read this rule a different way. I can parse it a different way, right? In particular, I could also parse it as like this. I could say P equivales Q equivales P, right? So this is this rendition right here, right? So this is a really nice property about equivales or equivalence. It lets you read the same rule in multiple different ways, right? So we'll get to this idea later on, but it's quite helpful. So here's a theorem. Let's show that P equals Q equals Q, right? Which is the same thing as showing this, for example, because of associativity, right? So we start here, and all I do is I flip two arguments, and I get P equals Q equals P, and this is symmetry, and we're done, right? So the top line looks strange. P equals P is the same as Q equals Q, and yeah, that's true, because P equals P is true, everything is equal to itself, and Q equals Q is true because everything is equal to itself, and true is equal to true, right? So that's another way to think about it, if you like. So here is the added parentheses if you're interested. So a small distinction, you'll notice right here, I have an equals sign, right? Whereas if I move, I can have a equivales sign, and equivales is just equality on the booleans. Okie dokes. Right? And because these things are always true, that means I can take the expression Q equals Q and give that a name. Because we said in the previous slide, P equals P, P equals P is the same as Q equals Q for any P and any Q, all right? Because these things are always the same, I can give them a name. So instead of calling it Q equals Q every time, I'll just call it true, all right? I'll call it true. So I gave it a name. This common expression, I gave it a name, all right? Incidentally, instead of saying, oh, Q equals Q is the name true, I can read this a different way, right? Because of associativity again, because of associativity, I can read it this way. And now this way it says, just like 0 plus Q equals Q, right? So it's like an identity log. That's why it's really important to learn these names, all right? So we used integers last week and most of this week to get you to be comfortable. But the idea is these names will be used repeatedly for the different operators that arise. And because the names are going to be used repeatedly, you actually don't need to remember so many theorems. You just need to know what the properties are, and then you know which operators have these properties, right? Because they're all essentially the same kind of formula, just for different properties, right? And you saw that in the homework when we talked about O plus and how O plus has a unique identity, right? Let me show you one calculation and then we'll conclude for the day, right? So just to use this true equals Q, right? True equivales Q, it means we can show that true is a theorem, right? So if we think of Q as being defined by Q becomes Q, this is a name now. We're introducing true to be this abbreviation for Q equals Q. And now we're going to show that true is a theorem, right? So we just use we use that rule to get for identity of true to introduce two truths. But then we said, wait a minute, true can be replaced again by the same result. But wait a minute, this same result is in fact this definition. So true is equal to this thing, right? But true equivales Q is an axiom, which is true, which is known, right? So I've been using the word true implicitly back and forth, but now we have an actual notion of truth to stand for this as an abbreviation for Q equivales Q. And we showed that this particular representation of truth coincides with what we think of as truth. So that's pretty neat, right? The way the world is and the way we think about it happen to be the same. All right. So my time is up. So I'll take some questions about the midterm if people are interested. Okay. Control C, Control Q. Okay. And yeah, thank you for showing up, and definitely please do the homework and the exercises and the assignment. It will definitely help you get ready for the midterm. The book has a lot of the answers. Okay, so if you decide, hey, I'm just gonna get stuff out of the book, you can get stuff out of the book, but the problem is you won't be as ready for the midterm. The midterm will have stuff that you might not find in the book, and it requires you to be familiar with manipulating formulae quickly. So if you decide to cheat, you really will be just hurting yourself on the midterm, which has a greater grade weight. Anyhow, bye. Unless you